Hello, welcome back. It's been a while. Here is part 2. This is the DC circuits section of our revision notes slash crash course slash whatever you want to call it. Last video we looked at electrostatics. This video we're looking at DC circuits. Beautiful box. And the following lesson we'll look at electromagnetism. Alright, so the main topics, not all of the topics, but the main topics in DC circuits are Ohm's law, right? You've learnt last year and probably the year before that. Total resistance, right, in series and parallel. Current and voltage calculations, like is it in a series circuit? So current stays the same, using that fact to then find voltage, so forth. Power calculations, right? P equals IV, maybe even relating it to energy or time. And finally, then linking power to brightness. That's a very common question because it involves all of the skills. So let's go through some of this together. I just need to fix that box because I know that's bothering some of you. There you go, you're welcome. Formula sheet. The first two, crisp. The first two, what am I trying to say? I haven't seen come up in any past exams really, maybe once or twice, but these are the definitions for current. So current is equal to charge per time. Charge per time. In other words, the flow of electrons, right? Depending on the size of the charge and how quickly it flows, will affect the current. Second equation, V equals change in energy per charge. So voltage, energy, change per charge. So I like to think of voltage, for example, if we have a battery, simple circuit. If you are a small packet of charge here, let's say your positive charge, at the bottom, at the negative terminal, you have no energy, right? You're at the bottom of the hill. As you go through the battery, there is a voltage across it, and you as a charge gain energy, right? You get taken to the top of the hill. So that's position 2. This was position 1. Now when you go around the circuit, you see a component like a resistor. There is a voltage drop across that, right? You lose energy. So now you've lost your energy, and now you're back to position 1, effectively. So voltage is the energy given per charge. When you come across that in like an exam situation, it's more just giving it as a definition. So you could just explain that voltage is the energy each packet of charge gains as it goes through a battery, or it's the energy lost per packet of charge as it goes through a resistor. Alright, let's move on to Ohm's law. And you're like, why is there a horseshoe? Well, that is omega, which is the unit ohm, right? That is the unit for resistance, because Ohm's law relates resistance, the current through it, and the voltage across it. For example, we have the most basic of circuits, let's say 10 ohms, 100 volts. If we know the resistance and we know the voltage, in this case the voltage across the resistor would actually also be 100 volts, right? Because these are connected in parallel effectively. We can solve for current as voltage divided by resistance, and in this example it would be 100 volts over 10 ohms, giving us 10 amps flowing through the circuit. And I drew it that way because conventional current flows from the positive terminal around towards the negative terminal. So you could think of an electric field sort of wrapped around or through the wire, right? From positive down to negative of the battery. So Ohm's law, again, relates the current through a resistor and the voltage across it. For example, if we know we measured 2 amps through some unknown resistance, so using an ammeter, and we measured using a voltmeter, right, connected across it, we measured the voltage as 6 volts, what would the resistance be? Well, resistance would be voltage over current, which will be 6 volts over 2 amps, which would be 3 ohms, right? 3 capital omega, 3 ohms. All right, and so Ohm's law is one of the most basic tools you have to solve simple DC circuit problems. Does Ohm's law always work? No. Right, and level 2, yes. But in reality, sometimes resistance changes, and this relationship isn't true. However, it is very, very useful, and it's still used in a lot of engineering applications. All right, Ohm's law. Nice. So that was, we looked at current and voltage, Ohm's law. Up next, let's jump to total resistance. Total resistance. So what is resistance? Great question, glad you asked. Is the opposition to current. Right? It wants to restrict the current that can flow through a circuit. So if you have a larger resistance, there will be less current through the circuit. If you have a very low resistance, like close to 0, you may have accidentally short-circuited something. That low resistance means a very high current. A very high current means a very high power / gets very hot enough that it might melt, and that's in fact how fuses work. Right? A very thin strip of wire that if the current exceeds its threshold, it will melt, which breaks the circuit. All right, so resistance in series. For example, series means one path for current to flow. If we have 10 ohms, and a 20 ohm resistor, the total resistance, RT, is simply the sum of the individual resistances. Yeah. So again, this isn't a full circuit, but you could imagine, if a battery is attached, right? These 3 resistors are in series. But I'm not going to draw the rest of the circuit, just to keep it a bit neater. What's another example? Well, I mean, how many examples do you want? It's all the same stuff. We go on forever, doesn't matter. The total resistance is just the sum of each individual R2 plus R3, so on. So that's for series. Wow, I didn't even recognize my straight line. What about parallel? Parallel. Let's do a parallel line here. Beautiful. Here we go. So parallel means there's more than one pathway. So notice I added these lines on the end to indicate, current could flow this way or current could flow this way. They are in parallel. Let's suppose they are both 10 ohms. I will show you exactly 3 ways to find the total resistance. The way you probably have been taught in class / is on your formula sheet is 1 over the total resistance is equal to the sum of 1 over the individual resistances. Right, that goes on for however many branches you have. In this case, 1 over the total is 1 over 10 ohms, that's the first branch, plus 1 over 10 ohms again, that's the second branch, and we're solving for RT. So to solve this, on the right hand side, add the two fractions. In this case, the denominators are the same, so it would be 2 over 10. But if they're different, don't try flex your year 9 or 10 maths, right? Just check on your calculator. Make sure you enter it correctly though. So have we solved for the total resistance? Nope. We've solved for 1 over the total resistance. So the last step is to invert. What I mean by that is 1 over 2 over 10. And the reason why we do that is, oh, too far. If we're solving for RT, we multiply that across, for example over here, but then we divide both sides by 2 over 10. Yep, like so. So if I just go back, hello, to this step, 1 over RT, our last step is just to invert the fraction, which is 10 over 2, which is 5 ohms. Now, how can you just double check, do a sanity check? Resistors in parallel, their combined resistance will be less than the resistance of the lowest branch. So let's look. What is the lowest resistance between these two? They're the same. So our combined resistance must be less than 10, which is 5. Great. Checks out. If we got more than 10, well, you did something wrong. So that's option 1. Yeah. Option 2, which is a shortcut. If the two resistors have the same resistance, the total resistance in parallel is just going to be half of one of them. Half of one. Is that in the screen? Yes. Half of 1. Wow. I don't mean like half of 1 times 1. I mean half of 1's resistance. Yes. English. In this case, it would just be half of 10, which is 5. Which is off screen, but you know, it's there. So that's only if R1 equals R2. So keep that in mind. And the final way, oh, do I confuse you? Yeah, I'll confuse you. I mean, help you. The final way is just like 1, but instead it's already rearranged for you. So the total resistance is equal to the product to R1 times R2 divided by the sum R1 plus R2. So this works for 2 resistors in parallel, right? Not 3, just 2. So in this example, 10 ohms times 10 ohms over 10 ohms plus 10 ohms, 100 over 20, which gives 5 ohms. Right? They all work. If you get a question, for example, with 3 resistors, strongly recommend you just use method 1, especially if they're, 4, 5, 6 ohms. Yep. So stick to method 1 for that. Or always, because it'll always work. All right, that's resistors. So in our tool belt so far, for circuit analysis, we know Ohm's law to relate voltage, current, and resistance. We know how to simplify a circuit, right? Combine the resistors in series or parallel. And now we can use those together to do current and voltage calculations, power calculations, and using that to explain brightness. So, I should have thought of some questions. Let's make a quick circuit. Those are in parallel, and then let's add a resistor here for good measure, not to scale. 10 volts. Let's just say all the resistors are 10 ohms. No, let's mix it. Let's challenge ourselves. 2, 4, 6, 8. Who do we appreciate? Me. You're welcome. Those are all in ohms. Now let's analyze the circuit. So find all currents and voltage drops across resistors. So a full analysis. And maybe even, yeah, we'll touch on power as well. So if you want to just pause the video and try it out yourself, right? Finding out the total current, the middle branch, the right branch current, finding the voltage drop across the 2 ohm, the 4 ohm, the 6 ohm, and the 8 ohm, as well as their power output. So pause and give that a go. All right, welcome back. If you didn't pause, shame on you, but let's continue. So analyzing a circuit like this, ask yourself, is it a series? Is it a parallel? Is it combined? I see this part that looks parallel, but within it we have a series, and all of that is in series with the battery and the resistor. So let's simplify the circuit by first combining the 2 resistors in series, then combine that with the one in parallel, then combine that with the 2 in series. So notice it's kind of like in maths, like bed maths, right? If you had like 2 plus 3 times 2 plus 4, you go in to the inner brackets. In this case, this is our inner bracket. Then you include the next stage, the plus 4, and then you include the final stage, in this case the 2. I just made up these numbers, but to illustrate a point. Get rid of those. So R S P. No. RS. The resistors in series, so the 6 and the 8. 6 plus 8. 14 ohms. So if we were to just draw the circuit again, I encourage you to actually do this. Draw the circuit again. But of course connect your wires, unlike me. 2, 4, 14. Right, we've simplified the circuit. What's next? Well, the parallel branch. So R parallel. I'm going to use a shortcut. The product divided by the sum. Oh, 56 over 18. Does that go in? 36? No, it doesn't. Where's my calculator? Divide by 2 a few times. 27. Wait, does it go in? No. No, 28 over 9. 3.1. You have a calculator. Alright, so we've simplified it yet again to our 2 ohm resistor and a 3.1 ohm. I've just dropped off the units, but bear with. Resistor. And now these two are in series, so the total circuit's resistance would just be 2 plus 3.1. 5.1. So, in summary, we've taken quite a complex circuit. We combined the 2 resistors in series that were in the parallel branch. We combined the parallel branch. We then combined the final 2 in series to get a single total resistance. Now, we can work our way back up the chain. But first, we can find Oh, there's my music, excuse me. 10 volts was here. We wanted to simplify it to one resistor to easily find the total current. As we know by Ohm's law, current is voltage over resistance. 10 volts over 5.1 ohms is 1.96 amps. So all the way in our top circuit, we know this first value for current, right here, is 1.96 amps. Now looking ahead, will that split into two? Will it split evenly? So if your current here, you look down, you see a 4 ohm, that's looking pretty good. You look to the right, you see 14 ohms ahead of you. Right, more of the current is going to go down the 4 ohm branch. It won't be half. So we just need to be careful about that. So how can we find that? Let's have a think. Can we find anything else with the current? Well, if we know the current through the 2 ohm resistor, we can find the voltage across it. Yeah. So where should I put it? Running out of room here. Didn't think things through. Room. Please hold. Just imagine elevator music. Hope it's sounding good. Yep, excellent. There we go. Alright, so let's find the voltage across the 2 ohm resistor, which will be the current times its resistance. So times 2 on my calculator gives 3.92 volts. So we now know that voltage, 3.92. Cool. So what would the voltage across the parallel branches be? We know in a parallel circuit they'd have the same voltage, so whatever this is, these two resistors would also have. If the battery provides 10 volts and 3.92 volts is lost across the 2 ohms, how much is left for the parallel branch? All right, we do 10 take away 3.92. So the voltage for the parallel branch, which is also the same as the voltage for the 4 ohm resistor, is 10 volts from the battery, subtract 3.92 volts from the voltage drop across the 2 ohms, which is 6.08 volts. So again, that is across here and across both the 6 and the 8. Not just one of them, but both of them. So it's like across the 14 ohms, effectively. Now, the reason we did this is actually called a KVL loop. You'll learn more about that in level 3. But anytime you go around a closed part of a circuit, whatever voltage you gain, so plus 10, you must lose across the other components. Because if you don't, we've broken conservation of energy. Because remember, voltage is energy per charge. Okay, what can you do next? Well, if you know the voltage across the 4 ohms, how can you find the current? Current, by Ohm's law, is the voltage across it divided by its resistance. 6.08 divided by 4, giving 1.52 amps. Now, does that make sense? Did we expect more current to go through that one? Yes, we did. So if 1.52 amps goes through the middle branch, how much current is left to go through the right branch? right? It's the difference between the total current and this branch current. So I, like 6 or 8 ohms, right, is the same, would be the total current, 1.96, take away the middle current, 1.52, 1.96 minus answer, leaves 0.44 amps. Great, what's next? Well, now that you know this current, you know the 6 ohm resistance, and you know the 8 ohm resistor, you can find their voltages. And I'll leave you to do that because I'm getting bored. And then power, since you know the current and voltage across each resistor, you can find the power by multiplying the current through it times the voltage across it. And power is measured in watts, right? Joules per second. All right, how are we doing for time? Oh, it's almost dinner time. Anything left? Current and voltage. I glossed over power, but I trust that you can multiply current and voltage. Usually the hardest part is finding the current and voltage, right? And lastly, we'll talk about brightness of bulbs. So actually, I'll give you a sneak peek at your homework, which is this question. The 2018 Electricity and Magnetism paper, question 3. For example, looking at bulb 2 and 3, notice how they have different resistance values, yeah? They will have the same voltage because they're in parallel. Which branch will have more current? Is it the lower resistance or the higher resistance? Right, it's the lower one will have a higher current. So if they have the same voltage, but bulb 2 has more current, how will its power compare to bulb 3? Right, it would be greater. And so how does its brightness compare? Power is analogous to brightness. Right, for a light, at least. The larger power output it has, the brighter it will be. Especially if they're the same type of light. Alright, so I'm going to leave this question for you to try. So feel free to either pause the video or look it up yourself. Here you go. Oh, we didn't really talk about ammeters. So I'll just give you a hint. It says with negligible resistance, which means it will have 0 ohms of resistance. In other words, this acts just like a wire, right? Like a short circuit. And here's a few hints in case you get stuck. You can pause the video, have a read of the hints. And here are the answers, 3 to 1. Total resistance, the series part plus the parallel part. Current, Ohm's law, using that Ohm's law again to find the voltage. A KVL loop like we did together. Touch on that. And the final one. Alright, happy studying.